Hello class, hope you are well. In this video we will be starting Chapter 7. And Chapter 7 we're going to begin with a review of an algebra property, which is solving linear inequalities and graphing them. And if just to sort of refresh your memory about this, probably something you've seen before, it's kind of where we draw the lines and then we try to figure out where do we shade, we shade here, here, here. And if you don't know or don't really remember what I'm talking about, that's totally fine because I'm going to be reviewing all of the how-to in this video and doing a couple examples of how we solve them and why. And I also want to focus on why does all this make sense, because how a lot of times I've seen people teach and learn this concept is kind of, okay, follow the steps, do this, this. But what I wanted to emphasize is, well, why are we doing all these weird things? What's the mathematical meaning behind it? And I promise this is actually very important for the next few sections in order to make sense of those. Uh, so we will be using this stuff, and like a lot of times in algebra, we learn how to do this stuff, but we don't really learn how it's helpful. But it will be important for the next few sections of the book. So let's just start with an example, and look at how we get into it. But basically, it's kind of like an extension of what we were doing in Chapter 6. Well, if we want to solve a system of equations, basically we're looking for the overlapping point. Where do they cross? What x, y, z point makes them all work at the same time? A system of inequalities is a little different because instead of having y equals this and y equals that, we now have y is greater than or y is less than. And all this means is it's a lot more flexible because instead of having to be exactly equal, it could be less than or greater than, and it actually creates a larger window of possibilities. So it's not like there's just one solution, which is fairly typical within systems of equations, but there's actually lots and lots of solutions. And the reason we graph and shade all those things is because we're trying to observe what region makes sense for the system. So let's start with the first example, y greater than or equal to 2x minus 3 and y is less than or equal to negative 3x plus 1. But basically, what we can observe is there are two lines here. Like we have a linear equation, and what I always suggest first is to start by graphing the boundary line. So looking at the advised step-by-step instructions that I have in the packet. Step 1, graph each boundary line. It says if it is less than, use a dotted line. If it is greater than or equal to, use a solid line. So in this example, we're going to be using solid lines to graph our lines, but I'll kind of talk about why we want to use dotted lines a little bit in just a minute. But basically, the boundary line is just it's not the same as the inequality, but it would just be the comparable equation, which would be y is equal to 2x minus 3, and y is equal to negative 3x plus 1. So basically, we want to start by graphing those equations instead of the inequality, because that will give us a sense of what are on the edge, basically. So y equal to x minus 3 is a linear equation. It has an intercept of minus 3 and a slope of 2. So we could do that. Let me try to graph this somewhat nicely. It has a y-intercept down here at minus 3 and a slope of 2. So rise 2, run 1, rise 2, run 1. Our line should be looking something like this. And basically, we're going to start by graphing each line. So this would be one of the lines. And I'm going to go ahead and label my graph just so that it's a little bit easier to follow. But that's the equation y is equal to 2x minus 3. But what I wanted to mention is how does the inequality, what is different about that? But basically what will happen is it's sort of like a normal inequality. So just sort of a quick review here, like y is greater, say we have x is greater than 2, right? In a simple inequality with one variable, it's kind of an idea, well, instead of x being equal to 2, right, like on a number line, if we want to know, well, where is x2, it's going to be, we just graph it by putting a point at its location. But if we want to know, well, where is it greater than, it actually opens up an entire range of numbers or domain or, whatever you want to call it, but an entire interval. And right, we often write that in the form of 2 comma infinity, just meaning that it's, well, any number larger than 2, or if it was equal, then, right, we use a bracket instead of a parenthesis to indicate that 2 is also part of this set of numbers. X is greater than or equal to 2. Sorry, very messy. This is the inequality I was working on. But my point here is that when we're moving into in linear inequalities with two variables, it's more complicated because I don't just have one variable. So instead of using a one-dimensional number line, we're using a two-dimensional graph here. The boundary line is kind of like the point where it equals, right? Like in x equal 2, I start with the dot and then I shade to the right. Well, with a linear inequality in two variables, I start with the boundary line, which is the line that controls, well, where is y equal to 2x minus 3? That's along here. And then I'm going to shade either above or below, or like you could think about it either as above or below or left or right. And then that's going to then I need to figure out, well, how do I know which side is going to be part of the graph? And one simple way to do it is if it's solved for y, it has to do with whether y is greater than or less than your equation. Because in this one, it says y is greater than or equal to 2x minus 3. Since this is where y is equal to 2x minus 3, and the y is, the y-axis is an up-down, if I want to know where is y greater than this line, it's going to be the region above it. So what I'm saying here is that this first inequality right here, y is greater than or equal to 2x minus 3, is going to be all of these values, not just the line itself, but every point in this larger shape. Basically half of the whole graph, or more than half. I mean, depending on what you mean by half. But basically all of this, if this is like a big field, there's going to be tons and tons of values that satisfy this particular inequality. And all the values down here do not satisfy it, as another implication of the shading. And usually if you're working with pencil and paper, what I recommend is shading it very lightly, because when we're dealing with a system, we don't that would basically be the graph of just one linear inequality. But if I also have a second linear inequality, that means I want to know, well, what satisfies both of them simultaneously. So let's throw in the second equation. The second equation has a slope of minus 3 and an intercept of positive 1. So it would intercept right there and have a slope of minus 3. So rise, run, rise, run, rise, run, rise, run. And if I was trying to solve just the system of equations, what we're looking for is where they overlap. So here, this would be our answer, because this would be where those two lines cross each other. But we're looking for more than that, because we're not trying to solve... That's really the only difference between a system of inequalities, is we're not just looking for the lines, we're looking for the shaded regions, and we're looking, well, at the end of the day, for where they overlap. And then looking at the second line, which is the line y is equal to negative 3x plus 1, we also want to know, well, that will also be shaded, since it's not really this. Really what I'm trying to solve is this original inequality, the system of inequalities. Whoops, hitting the wrong buttons. Which is this one right here. So really, we basically ignore the inequalities to graph the lines, but then there are shaded regions as well. And if I was going back to think about the shaded region for the first equation, since that was y is greater than all of that, we were going to have shaded all of these parts up here. But my point is, with the second region, let's go ahead and use green to represent the shaded region corresponding to that line. This one was y is less than or equal to negative 3x plus 1. And for the same reason, that equation is this one here. And since this y is less than, we could shade down. And this is one method of determining what region is going to be shaded in our graph. But actually, so the final answer, though, is we want to know, where is the doubly shaded region? Where do both regions overlap? Because thinking about the blue lines, that is the solution to the first inequality. The green lines over here are the solution to the second. And if I want to solve both simultaneously, it should be the position where both blue and green overlap in the graph. And notice that it's actually right over here. It's gonna kind of, I could kind of think of these lines as cutting my region into into 4 separate little spaces, and only one of those spaces, well, technically it doesn't have to be just one, but usually you'll just get one of those regions as being doubly shaded or overlapping. And basically, this is going to be our final answer. So actually, let me erase all of the shading because really the blue and the green are not our final answer. Our final answer should be where both regions overlap, which I'll do in purple. But basically, it's where y is above the line 2x minus 3, but also simultaneously below the line negative 3x plus 1, which gives us a particular region of space. And basically, this is going to be our answer. And this region over here, kind of this, this shape over here, technically it's going to keep going, but all of these numbers will all be solutions to the inequality. Now, there's an entirely different way of figuring out where the shaded region is. If that was a little bit hard to follow, or if it was kind of hard for you to see what I meant by above and below, there's a totally different way of doing it, which is how a lot of teachers will teach it. But basically, it is by guess and check. So let's go ahead and just do it that way as a method that, if some of you prefer, you can go ahead and figure out the shaded region that way too. But basically, once I have graphed my boundary lines, what I could do is I could test points in each of these 4 separate regions to see which one actually works. Because generally speaking, only one of the regions should actually be suitable. And if one point within the region does work within the system, all the other ones should as well. Because I don't want to really get into the why of that right now, but since each one is the boundary line, anyone that's greater or less should also be in that same region. But for example, we could just pick random points in the regions. I would generally pick points that are as easy as possible. Like this point will be really easy. This is this is the point 1, 1. And when I'm going to be plugging that number, those 2 numbers into the system to see if it makes sense. And I'll pick this easiest possible number. So like that would be 3, 0 would be in the right region. That's going to be pretty easy. Down here I could pick the point negative 6, 0. And in the left region, I could actually pick the origin. And basically, I'm going to pick a point in each region, and those are going to be my test points. What I'm then going to do is plug those test points into each inequality to see if it works. So let's go ahead and start with 1, 1, test point number 1, or I'll just go ahead and say t is 1, 1, and then we'll check that in our system. So the first equation stated that y should be greater than or equal to 2x minus 3. And what I have over here is a point x, y, so I'm going to just substitute in x and y into the equation. So y is 1, hypothetically, and x is also 1. So y should be greater than 2 times 1 minus 3. And looking at that math, 1 is greater than or equal to 2 minus 3. 1 is greater than or equal to negative 1. Definitely not in this universe, because every positive number, or wait, that is that is true. I had my inequality backward in my head. One is definitely, sorry, I'm a little tired. 1 is definitely greater than or equal to minus 1. So that's cool. But it doesn't need to just work in the first equation. It also needs to work in the second. Sorry, I said an equation. I meant inequality. It needs to work in the second inequality as well. So y should also be less than negative 3 times x plus 1, which would leave us with 1 is less than or equal to negative 2. That is definitely not true, right? Because every positive number is always bigger than every negative number. So what I can tell is that this point worked in 1. So this point right here, 1, 1, worked in the first one. And really, that's because that was above this line. It worked in that inequality because it was in its shaded area. But the second one, which was this equation, it did not work because remember that was supposed to be below and this one is not below. So this test point is out because it has to work in both inequalities to be a solution to the system. And I could repeat that process for every other test point until I found one that works. And if you try 3, 0 and negative 6, 0, sorry, this should be 0, negative 6, huh? Another really silly mistake because I'm tired. But those two will also not work if you want to try those on your own. But 0, 0, since it was in the solution area that we got from when I was talking about it before, should work. So let's go ahead and try that test point over here, just to make sure it indeed does work. So that test point 0, 0, I'm going to plug that into the original system. And again, I'm just picking, you can pick whatever point you want. I'm just trying to pick the simplest possible numbers I can. Typically, I'm trying to use values on the x and y axis, or values that include 1 or whatever. But basically, in the first inequality, I should have that y is greater than or equal to 2 times x minus 3. Or I have 0 is greater than or equal to negative 3. And that is definitely true, because 0 is bigger than any negative number. And then in the second inequality, I have 0 is less than or equal to negative 2 times 0 plus 1, since both x and y are 0. And that would give me 0 is less than or equal to 1, also definitely true. So what I can see is that this point, 0, 0, works in both inequalities, therefore it is a solution. And the implication is once I find a test point that works in both, I know that that is my shaded area of my system as well. So again, the point of this method is to figure out which area is shaded using a test point system. And once you guess, you basically guess and check. Once we find one that works, it implies the rest of the region must also work. In the next video, we will do another example of this, talk a little bit about dotted lines, and then we'll work our way up to chapter 7.2, which is on linear it's called linear programming, but we're trying to optimize solutions given a lot of constraints. And basically, why do we care about these things? Why are these useful? But essentially, such equations can often represent constraints in a real business situation. Say, for example, we're trying to do something, and we have to make sure that the number of x's and y's that we produce is less than 5 or greater than 100 or something. These sorts of graphs can help us to visualize a lot of different constraints going on simultaneously, and I'll try to get back into why these are useful when we get into that section.